We are moving forward, and our next talk is from my alma mater, Lomonosov Moscow State University. So Evgenia Kolenkina will talk about modeling of liquid displacement from the porous media, taking into account the presence of hydraulic fracture. So Evgenia, the stage is yours. Please go ahead.
Hello, my name is Kolenkina Evgenia, and today I would like to tell you about modeling of liquid displacement from the porous medium, taking into account the presence of hydraulic fracture. This report is about two-dimensional modeling of a two-phase seepage process in a porous medium containing a hydraulic fracture. The fracture is modeled as an area with increased porosity and permeability. We will consider the processes occurring in the horizontal section of the oil reservoir. In the area under consideration, there are an injection well, a production well, and the presence of hydraulic fracture in the area is possible. One of the difficulties of multi-phase filtration is the displacement instability. When a more viscous liquid is displaced with a less viscous one, displacing liquid tends to break through the displaced layer, forming channels called viscous fingers in it. The resulting instability leads to disruption of initially flat shape of the interface and the breakthrough of individual tones of the displacing fluid. This can lead to the entrapment of oil inside the porous reservoir and reduce the quality of oil displacement. In this slide, you can see some videos with our numerical simulation. This one is a three-dimensional numerical simulation of displacement process. Here you can see two-dimensional simulation. In the corners there are injection wells, and in the center of the area there are production well. In this simulation, in the center of the area there are also two hydraulic fractures. This video demonstrates the instability in the real experiment in the Heli showed cell, which is the simplest model of porous medium. We will solve the problem with the following assumptions. All liquids are incompressible. The viscosity of the displaced fluid is greater than the viscosity of the displacing fluid. Capillary effects at the interface are not taken into account. Permeability and porosity are location dependent. Thermal effects and gravity are not taken into account. The outer boundary are impermeable. Seepage is modeled by a Darcy's law, taking into account the relative permeabilities of the phases. Hydraulic fracture is an area of increased permeability and porosity, and permeability has a random ripple that contributes to the onset of instability of displacement. In this slide, you can see the mathematical model. First equation is mass balance. The second is Darcy's law. The summation of velocities of each phase is the average volume seepage velocity. The summation of this equation, taking into account this definition and the fact that all liquids are incompressible, leads to this equation. Darcy's law can be written in this form. After substituting of this expression into this expression, we obtain the equation for the pressure, and the saturation of each phase can be found from this equation. The relative permeabilities of each phase are modeled by Brooks and Corey model. As it was mentioned, the fracture is modeled as zone with increased permeability and porosity. And it is also worth to noting that permeability have a random ripple which provoke the onset of instability. Okay, the first model problem considered in this work is the process of cleaning a hydraulic fracture. The reservoir is initially saturated with pore fluid oil. There are 4 wells in the corners with constant pressure in it. In the center of the area, there is a production well and a hydraulic fracture filled with proppant and hydraulic fracturing fluid. It is assumed that the part of the fracturing fluid has leaked into the surrounding rock. Here it is assumed that the region pregnant with the hydraulic fracturing fluid is elliptical. Here it's the region A. The outer walls are considered to be impermeable. The viscosity of the fracturing fluid is greater than the viscosity of the oil, so the process is unstable. The purpose of the first numerical experiment is to investigate the effect of length of the fracture on displacement dynamics. 2 calculations were carried out with different fracture lengths. The calculation parameters are given in this table. Here you can see the dependence of mean saturation of hydraulic fracturing fluid in elliptic zone on time. The dependence initially behaves linearly and after that continues 2 degrees but never reaches a constant. The asymptote in this case is saturation equal to 0. So we can choose small and satisfactory saturation value as a criterion when it is considered that the fracture is already cleared. For example, if we assume that fracture cleaned when the saturation of hydraulic fracturing fluid reaches 0.2, it can be seen that the smaller fracture cleans up about 2 times faster than the larger one. In this slide, we can see the velocity of oil filtration at the same time for each case. The largest flows are observed in the fracture and near the production well. It can be seen that for larger fracture, the fluid flows faster in the area near the well. Here we can see the oil flux after 6 hours from beginning of cleaning. In the case when the length is 20 meters, the flow occurs along the entire fracture. In the case of a longer fracture, a breakthrough occurred in the area of production well. So in this case, at this time of moment, not the entire hydraulic fracture is involved on the seepage process. Here we can see the saturation of displacing fluid in the calculational area. Displacement instability can be observed. We can see the tones of oil break through the fracturing fluid. The breakthrough in the first case occurs in the fracture, and in the second through the zone near the production well. So in this case, the entire fracture will be put into operation later than in this case. After 15 hours, we can see that in almost the entire area, seepage occurs. The goal of next numerical simulation is to investigate the effect of fracture fluid viscosity on displacement dynamics. Two calculations were carried out with different viscosities. Here we can see how the saturation of the displaced fluid in the elliptical region changes with time. It is noticeable that on each graph, three parts can be distinguished. The first part is linear, the second is curved up, and the third is curved down. The first linear part ends, then there is a breakthrough of oil to the production well. After that, the section curved up, it is the time interval when the displacement velocity increases. This phenomenon can be explained by the fact that during this time interval, liquid is displaced from those areas that were not previously involved. You can see on the left side of the slide three pictures with the distribution of saturation at different time moments from this interval. In the last picture, we can see that the parts which were not involved in process previously are cleaned already. And the last part of this curve is when these hard-to-reach areas are cleaned and displacement again slows down. For these two cases, we can see that the difference is not significant. Through the entire cleaning period, the difference was no more than 3–4%. Here we can see the oil velocity at the same time moments for each case. And here you can observe the presence of breakthrough in this case and the absence of breakthrough in this case. Then the fracturing fluid has a high viscosity. A breakthrough through areas near production well is possible. In the case when the fluid is Newtonian, the entire fracture will be put into operation later. And in the case of Bergamo fluid, only part of the fracture will be connected to the seepage process. We can also see that for higher viscosity, the breakthrough occurs in the production well, but for low viscosity, no. It turns out that breakthrough for higher viscosity occurs earlier than for lower viscosity. The next problem under our consideration is unstable displacement of oil by water, taking into account the presence of hydraulic fracture. Here you can see two wells, injection and production. It is a possible presence of one or two hydraulic fractures. Low viscosity fluid such as water is pumped into this well. Oil is displaced due to the pressure drop across the injection and production wells. Oil viscosity is higher than water viscosity. Fractures are considered completely cleaned. The first numerical experiments is about effect of fracture length on displacement dynamics. It was carried out two numerical calculations with length of fracture 100 meters and 200 meters. Here we can see how the pattern of displacement has changed over time for each case. On the left, there is the fracture with length of 200 meters, and in the right side with 100 meters. You can observe the instability of displacement. On the left, we can see how the displacing fluid broke through the fracture to the production well. 3 years later, displacement continues, instability is not observed. And 6 years later, a large area is involved in displacement. Here we can see the dependence of oil saturation in production on time. Initially,
sorry, Evgenia, it would be really nice if you could wrap up in a couple of minutes so that we have a time for at least one question.
Okay, so I try to do it. Initially, only oil is extracted, but then the tons of water break through the production well. Mixture of liquids is extracted. Here, the dependence of the oil fast content in production on time is presented. We can conclude that the quality of oil in production, in the case when the fracture is 200 meters, decreases faster than in another case. Here we can see the total oil production. We can see that in case of 2 fractures, the total oil production is about 40% more than in the another case. The oil production per unit time for longer fractures is much more higher. And the last calculation is then the hydraulic fracture is absent. So here we can see the comparison for 3 cases, then fracture 1, 2, and without fracture. Here we can see that quality of production for cases of 1 and 2 fractures is not difference significantly, but it's much better for absence of fracture. And it can be seen that after 5 years of field exploitation, the total oil production is 3 times more in the presence of 1 fracture and about 4 times more in the presence of 2 fractures compared with absence of fracturing. And the oil production per unit time is the greatest for 2 fractures, as it was expected. And the main conclusions were already mentioned in the report, so thank you for your attention, and maybe you have some questions.
So thank you, Evgenia. We have a time for one question, I think. If somebody wants to ask, please either raise a hand or write it to the chat. I see Rostislav is willing to ask a question. Rostislav, please go ahead.
Yes. Yes. Hello. Can you hear me?
Yes, we can hear you.
Okay. So I just have a really small question. Probably you have mentioned this before, and I probably didn't hear it. Did you performed your calculations by means of some finite element method package like ANSYS or something else?
The calculation was performed by After's code. It was basics on finite difference method with 9 points template.
Okay.
Have you
Oh,
answered
okay. So it was a programmed.
self-written program? Yes.
Okay. Okay. So I see. Yeah. Well, thank you very much. Okay. Thank you.
So thank you. If you have more questions for Evgenia, you'd better handle it through emails or personal communications.